Hey guys, what's the crack? Can you see me okay? Potential divider circuits. Yes, we can. Hey Michael, what's up? Hey Sanjay. Tell me about time travel related to relativity theory. Tell you about time travel. That's not exactly A levels. You don't do that until you go to university. Did you guys hear? Pardon me, did you hear what I was just saying there? I just realized I maybe was talking before I even come on. But I was saying, hey Sanjay, hey Michael, relativity you don't actually do unless you try to do turning points in A-level physics year 13 or you decide to do at a university. So it's a university equation. And we want to mainly focus on things that's going to be in your GCSEs, mainly focus things that come up in your A-levels. Hey Pranav, what's up? Michael, yeah, you can get us started. So potential divider circuits. Let me see. You can tell me this what you're talking about, or you can give me an example of one you want. So potential divider circuits, let's start with this one. You mean a circuit like this, right? Is that what you mean by potential divider circuit, or what do you mean by potential divider? Potential divider just means that there's multiple paths, or, oops, sorry. Michael, give me like a yes or no if that's what you mean. Hey, James. Our favorite person. Hey, accelerator. What's the crack? Momentum. Yes, we can do momentum. I know. No, I actually did a good one with our class earlier. So just remember, if you are interested in joining our course, the MyEd Space course, there's a link in the bottom for you to like find out about it, or you can go to the MyEd Space website. But yeah, so we did a really good one accelerator in class the other day. Not the other day. Actually, probably was last month, but we'll do it after the potential divider. Okay, so let's look at this one. Let's do a theory one first. So let's say that the resistance, let's say that the resistance of the variable resistor is increased. Let's call this voltmeter 1, and let's call this voltmeter 2. What happens to voltmeter 2? Okay, pop in the chat if you can get that one. So the resistance of the variable resistor is increased. So I'm increasing the resistance of the variable resistor. What's going to happen to my reading on voltmeter 2? Let's pop in the chat. What's going to happen to my reading on voltmeter 2? James, I should be everybody's favorite person. What's happened to my reading on voltmeter 2? Decreases. Michael, I thought you said you had problems with this. That's easy. Yeah, good job. What are you having problems with then? Good on you. Okay, just in case anyone isn't as quick as Michael there, what we're saying is, here's my cell, right? So I know I've got my whole circuit. If the resistance of the variable resistor increased, you got to imagine you've got like electrons moving through your circuit, okay? So we've got our electrons trying to move through our circuit. And if we increase the resistance here, what we're doing is make it a lot harder for those electrons to get through. So if it's harder for the electrons to get through, they're going to lose more energy trying to get through it. So they're going to lose more energy trying to get through it. The potential difference here is going to increase, right? Because we know the equation E equals VQ, or potential difference is energy per unit charge. So if we've made this resistance really high, we've made it a lot harder for the electrons to get across. So they have to use up a lot more energy to get across, which is why that reading on voltmeter 1 is going to increase, okay? So if we know that voltmeter 1 reading increases, and we also know that our cell gives a certain potential difference. Let's say the potential difference was 12, for an example. What that means, each electron, if we again think about E equals VQ, or potential difference is energy per unit charge. Each unit charge, or each electron is coming out with 12 joules of energy, okay? And we know when they get here, they're losing more energy now than they did before. So they're losing more energy now than they did before. But they have two things to go through. So they lose more energy going through this component. They must lose less energy going through this component. So that's why the voltmeter 2 then, the reading decreases. It's going to go down. Yeah. Because that's probably like the hardest theoretical potential difference, potential divider equation I can think of. I'll give you another one actually. Oh, will we do one more? I think we should do one more. But let's do another one. Okay, so let's say I have this circuit. Okay, So what I can do is we can see this little arrow here. What it means is I can change where I connect the bulb. I can connect the bulb at point A, or I connect the bulb at point B. Okay. So I want to know what's a better circuit to get a range of currents. Is it going to be this circuit, or is it going to be this circuit? Circuit A or circuit B? So circuit A or circuit B? Which circuit is better for me to get a range of current through my bulb? Which circuit is going to give me a better range of currents through my bulb? A or B? What do you think? So which circuit is going to be a better circuit to give me a range through the bulb? Anyone want to be brave? Pop in the chat. So for example, let's say I'm trying to find out like the IV characteristics of a bulb, and I need to find like, I want a big range of currents to pop out on my, hey Fahim, on my graph. Which one's going to be a bigger range of currents? So think about electron movement. So electrons come out here in this in B, and they can either go through the full resistor, or they go through the full bulb, and then they meet up and they go back to the cell. Or here they come out the bulb, and think what happens as I can move this connection. Yes, Michael, it is A. Can you explain why though? So if I just look at A over here in a bit more depth, if we look at A, what we can really do, if you think about it, there's my resistor AB, the full length of it. What I can do is I can move the connection, move point X to be over here, right? I can move point X to be over here, in which case it looks exactly like circuit B. Or for circuit A, what I can do is I can move my connection so that it's here. So what have I done here to my bulb? So again, what we've done is we've moved this connection over to point A. So we've moved the connection to point A. What have we done to our bulb in this picture? What's going to be the current for the bulb in this picture? In this picture right here, what's the current for the bulb? So what's my current for the bulb in that picture? So you can pop in the chat, or figure out what I've done to the bulb. Maybe that's like a hint. What we've done to the bulb. So we've connected it right here, right at this end. Hi, Umar. What's crack? Call me ma'am. You from the States? So hopefully you're thinking, if my electrons come out here, when they get to this point here, they've got two choices, right? They're either going to go through, let's call this option 1, or they're going to go this way, which is option 2. If they go through option 2, you can see that they have to go through the bulb to get back. But if they go through option 1, they just have to go through the wire. So what we've done here is we've actually short-circuited the bulb. And if we short circuit the bulb, what that means is none of the electrons are going to do option 2, right? Because if you think about electrons, they have a choice. They either take option path 1, where they have no resistance, or 2, where they have resistance to the bulb. So what we do is short circuit the bulb. So it means all of the electrons are going to take option 1. So that means the current from my bulb there is going to be 0 amps, right? So that's why circuit A was better, because we can get a current of 0 amps up to a maximum current. Whereas here, you can never get down to 0 current for the bulb. So it's never going to get 0 amps in this bulb. So that's why option A is better. So it's like a bit of potential dividers, or thinking about how to use the circuits. Umar, we started with potential dividers, and now, hi Sarah. Now we're going to go to accelerator. Want to do momentum. Okay, so we're going to do momentum now. Yes, Sarah, we can. Okay, we're going to start with momentum 1. Okay, let's say, what we do. Let's say I have an asteroid. So an asteroid, and let's say it's got mass of 1,000 kilograms. Let's say it's moving at 20 meters per second, an angle of 10 degrees above the horizontal. Ah, Michael, I'm happy. And let's say this asteroid is going to hit Earth, right? So there's Earth. There's where we live. We're all happy on Earth. But we see the rocket coming, we get scared. Or we see the asteroid coming towards us, we get scared, right? Because if it hits us, there's going to be a problem. So what we do is we launch a rocket from Earth. And we want that rocket to hit the asteroid so we can move the asteroid. So let's say our rocket's got a mass of 2,000 kilograms, And let's say it's moving at a speed of 50 meters per second at an angle of 30 degrees to the horizontal. Okay. So what's going to happen then is when my rocket hits my asteroid, they're going to stick together and they're going to move away together. I want to know what speed do they move away at? Okay, so what speed do they move away at? So it's a momentum question. So see if you can figure out. So again, what we're saying here is we've got an asteroid going to hit Earth, but we don't want that to happen. So what we did instead is we launched a rocket from Earth to try and hit the asteroid to move the path of the rocket, move the path of the asteroid, so it won't hit us. So then once it hits the asteroid, they move together, and I want to see what V is, what speed is. Umar, good job. So what we know is momentum is always conserved. The momentum before must equal the momentum after. I always write before and after, but initial and final is the exact same, Umar. Yes, good job, Sarah, good job. So momentum after, if we look at our after situation, the momentum is going to be the combined mass. So it's going to be the mass of my rocket, which is 2,000 kilograms, and the mass of my asteroid, which is 1,000 kilograms, times whatever speed they're moving at. Okay, so let's look at our momentum before. So momentum before, hopefully you're seeing momentum is a vector. Okay, so momentum is a vector. So it's not as simple as going momentum before is equal to momentum after. Okay, so because it's a vector, we actually have to resolve it. We have to find what the initial momentum is in the vertical direction and then what the initial momentum is in our horizontal direction. So we'll just do it in two separate colors there. And then the momentum in the vertical direction gets conserved and the momentum in the horizontal direction gets conserved. So I've actually picked quite a hard example to start here, but if we do the hardest one, it's going to help, right? So what we're doing first is let's do our horizontal momentum. So before the horizontal momentum, remember, is mass times velocity. So we look at our rocket, we've got a mass of 2,000 and we want to do our horizontal velocity. And we go through the angle. The rule is the faster we do it, it's always cosine. So it's 50 cosine 30 because we go through the angle. So it's 50 cosine 30. But I also have my horizontal momentum of my asteroid. So I have my mass of my asteroid, which is 1,000 kilograms. What's that number? 1,000 kilograms times by the velocity of my asteroid. Remember, if we go through the angle, it's always cosine. So it's going to be 20 cosine 10. And what you should see is the horizontal momentum before has to equal the horizontal momentum after. So after the horizontal momentum, right, we know this rocket's going to move at some speed, okay, and it's going to move at some angle. So I know its horizontal momentum is going to be its mass, which we said was 3,000 because they're stuck together, times by its horizontal, which is going to be phi cosine 30. Because I don't know what that angle is, and I don't know, oops. Oh, that's annoying, sorry. I went too high in the screen. We don't know what the angle is either. We don't know the speed of the angle because remember, velocity is a vector. So this one's going to be phi sine 30, or sine of theta, sorry, because we didn't go through the angle. So we're seeing the horizontal after is going to be 3,000, which is our mass, times by phi cosine theta. Okay. Then let's set up our vertical motion. So I hope you're thinking for the vertical motion now. I hope you all try this with me. So actually help me out then. What is the vertical momentum of my rocket? What's the vertical momentum of my rocket? What's the vertical momentum of the rocket? So I want to do mass times velocity. So the mass of my rocket times the speed of my rocket. What's the vertical speed of the rocket? Yeah, good job. So I hope you're thinking, if I don't go through the angle, it's like a sin against God. So it's going to be phi sine, not phi, sorry, 50. Because it was going at 50. 50 sine of 30. And if I have to add on our vertical momentum of our asteroid, which is our mass of our asteroid, times by 20 sine of 10. Because if we don't go through the angle, it's always a sin. And that must equal the vertical component finally. So the vertical component finally is my mass of them joined together times by phi sine of theta. Okay. So does anyone see what we're going to do here? How are we actually going to find out? I've got V and cosine theta, V and sine theta. So a lot of you did the math. So see if you can do the math and figure out what it is. So this is probably the hardest question I've ever seen on momentum, but I think it's quite good to do a hard one. Yeah, good job, Emma. You would divide both equations. Good job. So all you would do is you solve for this line, this purple line. So if you solve for the purple line, you should get a number. If I'm just doing it in my calculator now. Does someone want to solve for the red line for me if I solve the purple line? 20 times by cosine of 10. Can you agree with me? Do we get the purple line here? So the purple line is 106,298.7. And the red line, did anyone get the red line? To be 2,000 times by 50 times by sine of 30. And then we have to add on 1,000 times by 20 times by sine of 10 to get 53472.96. Yeah, and then exactly what our last step then is to do what Emma said, which is perfect. So if you think about it, what we really have now is 106,298.7 equals 3,000 times by v cosine theta. And I know that 53472.96 equals 3,000 times by phi sine theta. And if we divide them, good job. If anyone remember the rule, sine theta divided by cosine theta always gives us a tan theta. So if I flip these around and divide them, what I have now is 3,000. I'm going to do 3,000 times by phi sine theta divided by 3,000 times by phi cosine theta to get that it's going to be 53472.96 divided by 106,298.7. My 3,000s cancel, my v's cancel. Sine theta over cosine theta is tan theta. And I can see tan theta then is just going to be 53472.96 divided by 106,298.6 to give us tan of theta is going to be 0.5. So theta, I just have to do my inverse tan, shift tan of that answer, and we'll figure out that it's going to be an angle of 26.7 degrees. So I figured out that angle there above the horizontal is 26.7 degrees. And now all I have to do is pop that angle for theta into my equations, and I can solve for what v is then. Because if I pop in theta now, I know theta is 26.7. So I pop it into this line of math, I can solve for what my phi of my rocket, my head's in the way, what my v of what my rocket and my asteroid is together. I think I love that question because it's not like a simple momentum question. So Emma, thank you for staying with me for it. It's not like a simple momentum question, but you really have to think about momentum before and after is conserved, but you have to actually separate your horizontal and your vertical motions because momentum is a vector. So when it said to find the final speed, you had to realize that it is some angle as well. So again, we've got two equations with two unknowns. You do exactly what Umar said. You divide them. And remember that math rule that sine theta over cosine theta is always tan theta. So I quite like that question. We did this actually on our online course as well. I don't know if Michael, I think you were there. Don't know if you remember this. Or Michael, Michael shouldn't me, but I can't remember if you're not year 12, maybe not year 13, I can't mind. Trigonometry, Sarah. Okay, Sarah, I'll give you a quick recap of what you need to know for your trig identities. Okay, so for trig, I know Pythagoras is what everybody loves in maths classes, right? I know everybody loves doing this big triangle and the square and doing like SOHCAHTOA, right? And always resolving this way. That takes you too long in physics. You have barely any time in physics. The best way in physics is just to learn like a really simple rule and it always applies. Let's say that's my force and that's my theta. If you always go through the angle, it's always going to be cosine. So if I went against the angle, like against God, it's always going to be sine. So that's the main trig rule you have to learn. You don't have to learn the whole SOHCAHTOA thing. Just learn this fact. And it applies any way you do it. So let's say my force is here now. And there's my theta. If I want to find out what the horizontal is, through the angle is always cosine theta. And against the angle is going to be sine of theta. It's always the same rule. And the other trig rule that you need to learn is you just need to always know that sine theta over cosine theta gives you a tan theta. That's literally the only two rules you have to know. But this one comes up quite a lot in physics. So that one you do need to know off by heart. You don't need to know any of the other ones. Okay. Umar comes in basic math directly, but it's a lot of application in physics. Yeah, it does. So again, you don't have to ever do like the Pythagoras rule in physics, apart from, yeah, you do need to know that a squared is equal to b squared plus c squared. So you do need to know, yeah, a squared is equal to b squared plus c squared. But you don't have to do like SOHCAHTOA ever. You just have to remember this rule. Through the angle will always be cosine. Against the angles always be sine or like sin. I saw James, efficiency. Efficiency with what? Like, what are you talking about? James, you're GCSE, right? Efficiency, do you mean like with transformers or like a general energy efficiency? Efficiency. And I saw someone else ask me a question about something else. Dampening. Yeah, Sarah, sorry, I forgot about your dampening. Okay, dampening. So, how do you think about it? I think a pendulum is probably the easiest to think about. Okay, so let's say you've got a pendulum. A pendulum is in its swinging, okay? So if we look at the amplitude over time, okay? So does anyone know the different types of dampening? There's 3 main types of dampening. So basically what we're having is, if a pendulum had 0 dampening, its oscillations would have the same amplitude all the time, okay? But that's not what really happens in life, right? Because we know if this is oscillating, it's not in a vacuum. If it was in a vacuum, yeah, the amplitude would never change over time. But it's not in a vacuum, right? It's normally in air. And if it's in air and it's trying to move in this direction, we've got air particles hitting the pendulum, so trying to slow it down. Yeah, Sarah, good job. So there's light dampening, there's critical dampening, and then there's heavy dampening. So the different types of dampening, okay? So if we just look at how this graph would change. So let's say I've got light dampening. That's what happens actually all the time. So it's not in a vacuum, it's in air. So what's happening is there'll be a force of those air particles on that pendulum trying to slow it down. So it's trying to oppose its motion. So its amplitude might be really high at the start for its first swing, but then its amplitude will start to decrease over time because of the air resistance. So its amplitude keeps decreasing over time, decreasing over time, decreasing over time, until the amplitude eventually stops swinging, okay? So that's what your light dampening is. It's like just something in air. Critical dampening just means we want to get it back to the equilibrium as fast as possible. So critical dampening is want to get back to equilibrium as fast as possible. So let's say we went to our maximum here. We want to go back to the equilibrium as fast as possible. Okay, so that's what your critical dampening is, how you get back to equilibrium as fast as possible. Heavy dampening might be we put it in something like oil. So if we stick this pendulum in oil, if we stick it in oil, once we get it to its maximum amplitude, it's going to take a really, 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 really long time to get back to that 0, right? So if you imagine we stuck this pendulum in oil, it's going to just go really, really slowly, or really thick honey. It's going to really, 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 really slowly until it ends up back at its equilibrium. And then once it gets there, it's just going to stop moving because we've put it in either honey or oil, something that's got a big force on it, slowing it down over time. Bernoulli's theorem and its equation. Amir, can you give me like an application for me? Transformers. Why is work done positive to move an object further from a planet? Is it in Hoa? In Hoa? Hello. We did this actually one time before. It's like a common question. So yeah, we will go for it. Let's say we got planet Earth. Okay, so what you're saying is, why is the work done positive to move an object from a planet? Okay, so you've probably seen the equation work done. So work done is, or have you seen potential? So the gravitational potential is the amount of energy required to move a mass from infinity to a point in the field. Okay, so that's what it is. So gravitational potential is the work done per unit mass, because we know gravity's got to do with masses, to move something from infinity to a point in the field. Because infinite far away, like extremely far away, we say things have like 0 energy. So the potential there is 0, right? So let's say I've got some mass, Let's say we've got some mass, some 1 kilogram mass. And we know Earth has got a massive mass, right? The mass of the Earth. I know that 1 kilogram mass gets close to the Earth. Gravitational pull of attraction will try to pull it towards the Earth, right? So I don't have to do anything because gravity wants to be attractive. Gravity is always attractive. It's going to try and pull it towards the Earth. So I don't have to put any work into the system. It's actually negative work, right? So no work has to be put into the system because it wants to go towards the Earth. So that's why when you do this topic, all the potential lines around the Earth, they're all negative lines. They're all negative because gravity wants to pull the mass towards the Earth. So for example, let's say we're doing the opposite way, like you said, Inuba. Let's say we have a mass here and I want to do the opposite. I want to remove it from the Earth. Because we're going in the opposite direction, gravity wants to pull that mass towards the center of the Earth. So that's what it wants to do. So if I want to get the mass removed from it, if I'm trying to pull it away from that attraction, I have to put work in to remove it. So that's why when we want to remove the mass, if we're trying to remove it, we have to put work into the system because they pull against the gravitational pull of attraction. Yeah? Umar, I just saw your answer. That's like basically exactly what I just said. That was perfect. So the work done, to find the work done, you always just do the gravitational potential times the mass. Do you see? So the equation on, if you're doing AQA, that's the equation in your data sheet, and it looks very similar in OCR and in Excel. So to find the work done, you do the gravitational potential times the mass. And gravitational potential is always going to be, if I remember off my head, G mass 1 over the distance between them squared. They just have to multiply by mass 2 to find how much work you need to put in. Wait, let me remember if that's right. F equals G M1 M2 over R squared. So the gravitational potential is over R, over R. So yeah, gravitational potential is Gm over R, okay, where do we get to? We got 3 minutes left, so what have I got? How would you have a shadow? Umar, did you not ask? Oh, someone asked about shadows again. Yeah, someone. Hooke's law, 100%. I've got 2 Hooke's law. Right, we'll do a quick, We'll do a quick Hooke's law. Is it Hooke's law GCSE or Hooke's law A level here? What are we talking about? GCSE, yes, grand. We got 3 minutes left, that's perfect. Okay, so Hooke's law, actually, if you're in A level, you can help us out. Hooke's law is this. So what it means is that this symbol means directly proportional. So what it means is force is directly proportional to extension. So what it means is force equals some constant times by extension. So what you need to know in GCSEs, the problem is the word extension. And that's the problem every year. The word extension, all it means is change in length, just a fancy way of saying change in length. So what we're saying is if we apply any force to a spring, because the constant becomes spring's constant, if we apply any force to a spring, we're going to get an extension or a change in length. So let's say we've got a spring hanging here. If we apply any force to it, if we pop mass on here, so if we pop any mass, let's say we pop 100 grams on it, we know gravity tries to pull that mass down. So we know W equals mg, weight is mass times gravity. So let's say we use G as 10 on Earth, we know the weight then is going to be 1,000 newtons. And what we can see is if we apply that mass, my spring gets stretched. So what I can see is my spring was originally here, but now my spring is here. So that change in length there, that's my extension. And when we plot a graph of our results of force against extension, and this actually comes up in A level as well, force against extension, what you can see is you get a straight line through the origin because they are directly proportional up until the limit of proportionality. And you have to know that definition for A level as well, actually. So for Hooke's law, force is directly proportional to extension up until the limit of proportionality. And then after that point, we've gone beyond the elastic limit. It's no longer elastic. We say it's plastic. So if I was to remove those weights, we can see if we take the line back, and in A level, you have to remember the line goes back at the same gradient as the first line. You can see that the final length is no longer 0. It doesn't go back to its original length. It's permanently deformed. Yeah, and then like Umar said, if you want to then boost that up to A levels, you don't do force against extension, we do stress against strain. And then the gradient of that graph is called Young's modulus. And again, you still have to know the same definition, that the force applied is directly proportional to extension up until the limit of proportionality. Yeah. Guys, loads of interaction today. That was great. So I actually really like that. So just remember, if you're on the if you did like the GCSE stuff, so we're going to do this every week, so we get half an hour. But again, it's kind of mainly based at A levels. That's why if you're doing GCSE, you're probably like, what's going on there to start? But it's really nice, I think, for you guys to see what A level could be like. And again, if you have any questions about like universities or what you're thinking to study or what is teaching like, what jobs can you have as physics? Just always like pop in the chat, and it's like as soon as I see them, I can help you out. Yeah. So hopefully I'll see you all next week. And thanks for joining and for being like really active with me. And remember to sign up to our newsletters as well, because if you sign up to the newsletters, we always like give you like some extra revision sources for free, which is really helpful, especially if you're in GCSEs or in A levels. Yeah. But love to meet y'all, and thanks for your time. And I shall see you later. You're so welcome. Thank you for joining. Bye.